Hi, this is lesson 27 in the use of JASP for understanding statistics. And today we're talking about the One Factor ANOVA, continuing on with a couple of lessons that I've done the past couple of rounds. And today we're going to talk about the difference between a priori test and post-hoc test and show you how to do some contrast coding. So let's get going. Let's start by clicking on our three bars, go to Open, Data Library, and we're going to go to Analysis of Variance. We're going to pick up that same data set that we've been working on the last couple of lectures, which is pain thresholds. We're going to load that in. I am going to get rid of everything that is there so that we can start fresh. And there's the data set. Again, this is looking at the relationship between hair color and pain tolerance. Pain tolerance, for example, would be how long could you hold your hand in ice water enduring the pain? Higher numbers, greater pain tolerance. And we have four groups of people who have either light blonde hair, dark blonde, light brunette, or dark brunette. And to do a one factor ANOVA, we go to ANOVA. We put hair color is our between groups or between treatments factor. Pain tolerance is the scores. This is discussed in greater detail in my previous video. Here is the ANOVA table. It gives you the between groups line and the within groups line. Calls the within groups line residuals, and it's showing that there is a significant F-test. You always want to look at your descriptives, and here's the descriptives, and it seems to be showing that the dark blonde and light blonde have higher pain tolerances than the brunettes. There's other, that's even higher for the light blonde person. Which one of these effects is significant? That's the question. So there's two ways of going about determining that. We talked about this in my last lecture and focused on post-hoc test. Now, the idea of post-hoc test is that it assumes that the researcher doesn't have strong justification and expectations for where the differences lie. And when you have 6 groups and you start comparing each one of those means together, there's 6 possible comparisons. Dark blonde versus dark brunette, dark blonde versus light blonde, dark blonde versus light brunette, dark brunette versus light blonde, dark brunette versus, and light blonde versus light brunette. 6 possible comparisons. And the more comparisons that we do, the more tests that we do, the more we risk inflating the type 1 error. In other words, getting some type of difference by chance and getting a false positive. So I'm going to run through post-hoc tests just real quick again, but today I want to focus on the contrasting a priori test. So to do a post-hoc test, go to post-hoc test, hair color. The most common one, as we talked about, is the Tukey's, and you can flag the significant comparisons as we talked about before and look at the letter-based grouping. Okay, what it does is said there's 6 possible comparisons. It's close to finding a difference between dark blondes and dark brunettes, but it doesn't find that difference. Notice that the p-value is 0.074. It needs to be below 0.05 in order for it to be significant, so that's considered non-significant. You have 2 significant comparisons, but you have a third that could have been significant. Why is it doing this? Why is it coming out this way? It is coming out this way because there are adjustments in this statistical procedure designed to say, I don't want to say that there's a significant that this difference of 13.8 is significant if it could have been obtained by chance. So it's controlling for, again, that false positive rate going up, because the more you do, the more that you're going to risk finding something by chance. So this procedure turns out to be less powerful compared to if you had strong theoretical expectations. Now, the other way to go is what are called a priori tests. And you'll find a priori test under contrast. So contrast is basically saying, I'm going to expect a certain pattern of results. If we go ahead and say that we want to do a contrast, it shows multiple contrasts here. Let's just click on the first one, deviation. And it comes up with this deviation. And there are things I like about this output and things I don't like about it. I don't like that it doesn't actually display for you the contrast coding that goes into this. But the thing that I like about it is that, even without the contrast coding, it does tell you what it's comparing. And here it's comparing the dark brunette against the dark blonde, dark brunette, light blonde, light brunette. Well, that's odd that it's comparing the dark brunette against the dark brunette. If you look through this list, all of these basically are the same. In fact, all four groups are listed. And the idea is that if you take the average of that, you have the grand mean. The mean tolerance level across the whole sample of participants, regardless of what group it is. So what this test is doing is it's saying, I'm going to take my first three groups and I'm going to compare them against the grand mean, and then gives you the significance for that. Now, I don't find that one interesting. And most of the time, I don't like comparing against the grand mean. Let's go to one that I do find interesting, and I'm not going to try going through all of these, but if you're on JASP, you can actually play with these. You can do the simple, the difference. I'm going to go with one of the classics, which is a Helmert. And what the Helmert is showing here is it has dark blonde compared against dark brunette, light and light blonde. That one is not significant. It has dark brunette compared with the average of the light blondes and the light brunettes. That one is statistically significant, showing that the dark brunettes, the negative, has less pain tolerance than the other two groups. And then you have light blonde versus light brunette, and that one is significant. Let's pick this light blonde versus light brunette. It is significant at 0.008. Over here for the post-hoc test, you also had light blonde versus light brunette. It was only significant at 0.037. You'll notice again that the post-hoc test is being more conservative, whereas the contrast is giving you more power. So when you find significant results, you'll notice that they tend to have lower p-values, indicating that they're quote-unquote more significant, if you want to use that phrase. Okay, but these comparisons are not ideally what I would have gone with, not at all. What's going on here? Well, let me show you a layout. I'm going to go over here to what I laid out in Excel. So in Excel, what I've done is I'm showing you here, let me zoom in some. Here is what the program is doing. The means, the groups were ordered in this fashion, and a Helmert set of codes Basically, it goes 3, minus 1, minus 1, minus 1. Why 3, minus 1, minus 1, minus 1? It basically is taking the 3 as a positive for the dark blonde group, that 51.2, and comparing it against the 3 others averaged together. You'll notice that minus 1 plus minus 1 plus minus 1 gives you negative 3. Then the positive 3 balances out against negative 3 for the other group, all combined. That is a contrast code. And the second contrast that it does is, I don't have this one color coded over here because the colors change each time. So it's only color coded over here for the first contrast. But if we were to do the second contrast, I'll take off the color codes. It would ignore the first group. Then it would take the second group and compare it against the next two groups. So you have 2, and then the minus 1 adds up to minus 2, which balances out the 2. And so it's basically saying I'm going to weight this group with a positive 2, these two with negative 2s, so that I get an equal weighted comparison between one combined group and one single group. And then finally, it compares the light blonde with the light brunette. So the Helmert contrast comes out this way. A rule about contrast coding. There's a number of rules. I'm going to only very quickly kind of give you a hint as to how that works. And the first one is that a proper set of contrast codes will always sum to 0. So this column added up, it sums to 0. This column added up, it sums to 0. This column added up, it sums to 0. 1 plus negative 1 is 0. So they have to sum up to 0. Okay? So there is that. What is happening here is that it's basically saying if you take this first group, the dark blondes, and compare them with the other 3 groups, then any other comparison of the dark blondes with other groups would be redundant. So you can't have that. So then it zeroes out the dark blonde group and says, I'm only going after unique independent contrast. I've compared dark blonde to every other group. Therefore, dark blonde is out of the equation. But in contrast 1, all of the other groups were treated as the same. Since all other 3 groups were treated as the same, now I can start looking for differences between them. And so then it takes and puts a 2 on the dark brunette and says, I'm going to look at dark brunette versus these 2. Once you're finished with that contrast, it says, I've done everything I can with dark brunette that is unique, that is independent from the others. So I'm going to zero that one out. These 2 groups in both of my previous contrasts have been treated as though they're equal to one another. So now I'm going to look finally and see if those are different. Okay? That's how the Helmert contrast coding system works. And it's a good contrast coding system. The problem with it, however, is that it always just lines up exactly like this, which means that if you want meaningful comparisons, you have to order the groups in your data set. You got to convince JASP to order the data set such that it lines it up in the way that you want. And it's not doing that. So I like to use custom. I still like the Helmert coding system. And so what I would do is I would say theoretically, it looks to me like the expectation is that the lighter the hair color, so blondes should have more pain tolerance than brunettes, and hence, if it's a lighter color, light blondes should have the most. So I would start off with light blondes as my 3 and compare it against all the other groups. And then once I did that, then I would go to dark blonde and compare against the brunettes. And then last, I would go to see, is there any difference between the dark brunette and the light brunette? And hence, I would use the Helmert contrast coding system, potentially, but I would enter it as a custom coding system. Here's how you do that. So go over here, custom. And then it gives you, sets you up for the first contrast, and I would go 3, -1, -1, -1. Okay? And then I'm going to add my second contrast. And my second contrast, I said, would be the dark blonde against the brunettes. So I'm going to do a 2, a -1, and a -1. And I'm going to leave the light blondes as 0. And then I'm going to add my third contrast. And I'm going to put zeros where I had the 2 and the 3. And I'm going to compare the light brunette as 1 against the dark brunette as -1, because I'm working on with the hypothesis that lighter color is more pain tolerance. It's not absolutely necessary to line it up in terms of the positive and negatives. You can always look at the means to interpret it, but I like to try to line it up. Okay, click somewhere else on the sheet, and it allows the contrast to show up. And here it is showing me that my first contrast, comparing the light blonde against all the others, is statistically significant, and the p-value is even less than the p-values I got from the post-hoc test, consistent with the idea that it's a more powerful test. So you look at the second one, and it is showing that the the dark blonde is statistically significantly different than the brunettes. That was not shown before. Before we had the dark blonde against the other groups, and those were not statistically significant. Like dark blonde versus dark brunette for the post-hoc was not statistically significant. So this is definitely a more powerful test that is showing you that the blondes, both of the blondes, have higher pain tolerance than the brunettes. So if you have that precise theoretical, you use contrast weights not to take advantage after looking at the means, but if you come in with a theory in advance, it's like at a pool table, the person calls their shots. So if I say, I'm going to shoot this ball, bank it someplace and get it in the left corner pocket, then I only call the shot, and I only get to claim the shot if it lands in that left corner pocket. If it lands someplace else, then I say, nope, I'm not counting that, right? So that's the idea of a contrast. It's basically saying in advance, before I take my shot, before I conduct the study, I'm basically specifying that I think it's going to be the blondes are going to have higher pain tolerances than the brunettes. And so I'm going to give myself this extra statistical power of doing these planned contrast. And when you do that, you focus precisely on the planned contrast, and the actual ANOVA table kind of goes to the wayside. You can just go directly in and just report your planned contrast. And if you have a complete set of orthogonal contrast, and this is a complete set of orthogonal contrast, it gets all of the unique um, comparisons within the system that you've created, then you've covered your bases. And you basically can talk about the blondes being different than the brunettes, but the brunettes are not statistically different from each other. Okay, so that is the Helmert contrast system and my first foray into planned contrast. And I'm going to come back and do another one. But I hope that that helps explain the difference between post hoc test and a priori planned contrast. Thanks for listening.